shapes of molecules, and we're going to look at polarity now. Molecular polarity occurs under a set of circumstances. Molecules are either polar or nonpolar. So molecules are polar when they have polar bonds, and the molecules are unsymmetrical. So you have to have polar bonds and lack of symmetry in order to be a polar molecule. Molecules can be nonpolar when either they have no polar bonds or they have polar bonds and the molecule is symmetrical. So the symmetry allows the vectors of the polarity to cancel each other out. So here we have a trigonal planar BF3. The bonds are polar, but the molecule is perfectly symmetrical, and we look at symmetry as going through a bond. HCl is polar. The bond is polar. The molecule is unsymmetrical. So this one, the rule of thumb is it doesn't matter how many planes of symmetry you can draw. If you can draw one that's not symmetrical, then the entire molecule is not symmetrical. So if we look at this one, we can rotate it to where these two are in a bond, in which case you're going through this bond here, and it's unsymmetrical there. This one, if you look at it, you can draw the plane of symmetry right there, and it is unsymmetrical. So that one's polar. Carbon tetrachloride has polar bonds, but is perfectly symmetrical, so it is nonpolar. So when we're looking basically at polar molecules, we look at the individual bonds, but then we look at the overall symmetry of the molecule. Since we have no symmetry here, then it's going to be polar. On this one, we end up with a larger negative over here than on this end, so this one is polar. And we say because it has a lack of symmetry, it has a net dipole. On this one, because a tetrahedral is perfectly symmetrical, there's no net dipole. So this one is nonpolar. This is the carbon tetrachloride, which consists of polar bonds and nonpolar molecules. So it produces a nonpolar molecule. You can look at polarity if you want to look at it with the electron density scale. For a linear molecule like CO2, it's perfect. It has negatives here, but they balance each other out. Whereas if you look here, this is symmetrical this way, but it's not symmetrical this way. We're red here, blue here. So again, you can draw 100 planes of symmetry. If you draw one lack of symmetry, then it is going to be polar. Remember, the magnitude of polarity is measured by dipole moment and the distance between the charges, and you have a dipole moment, which is charge times radius, and the unit is debye. Pointing this out because you will use this in organic. Now, why is this important? Because polar molecules have certain properties. You'll find later in 1212 that polar molecules have lots of interactions with each other. The other thing they have interactions with is electric fields. So if you put molecules in between two electric plates and turn on the electric plates, This one's positive and this one's negative. Notice that the molecules go from an uneven distribution to basically lining up across the space. Why is that important? Well, when you have filters in your house and they have the electrostatic grate that you can pull out and wipe down, all they're doing is picking up polar molecules as it goes through. Okay? So now we're going to identify the polarity of each of the following molecules. And if you'll notice, we've done all these. So I was able to import them so you can go back to your notes. I told you we were going to come back to them. And I want to make sure I do this in a different color. So I'm going to use polarity. It's going to be in blue. So the next question here is the polarity question. So if we look at these, they have polar bonds. So all bonds are polar. But the molecule is symmetrical. It's a perfect triangle, so it's perfectly symmetrical. So this molecule is nonpolar. Trigonal planar, all 120, nonpolar. Okay, this one again has polar bonds because carbon fluorine bonds are polar, much like carbon tetrachloride. But it's a perfect tetrahedral, so it's symmetrical, which means this molecule is non-polar. This one has polar bonds again. It's an octahedral, so it's perfectly symmetrical. When you look at the symmetry, you don't look at the electronic structure, you look at the molecular structure. So we're going to find out that this one is nonpolar as well. So this next region here, we're going to have polar bonds. But remember, this is a T-shaped molecule. So this is a polar bond, this is a polar bond, this is a polar bond, and this is just air. So this is unsymmetrical. So with polar bonds and lack of symmetry, this is a polar molecule. So in this shape, we're going to have polar bonds. And we said that this was a seesaw. So a seesaw looks like this. So if you look at it, there's empty space up here, so there's no symmetry. So this obviously is a polar molecule as well. Carbon-sulfur has polar bonds. The molecular shape is linear, so that means the negatives are perfectly balanced. So this is a nonpolar molecule because it's perfectly symmetrical. Okay, this region here, this one has polar bonds, and it is trigonal pyramidal, so it's unsymmetrical. So it's going to be polar, right? No. This one's a trick question. It's an ion. A polar molecule is a molecule that has an uneven distribution. An ion has a full charge, positive or negative. So if you're asked for polarity and it's an ion, then you say it's an ion. Okay, so I did this up here for you to see in case it wasn't an ion that you could carry this through. Same thing here, we have polar bonds. It's square pyramidal, which means you have the square pyramid here. And so you have this empty space down here, so it would be unsymmetrical. Again, this one would be polar if it was a neutral molecule. It's not. Again, it is an ion. So when we look at these problems, we look at them from the viewpoint of whether we have a polar molecule, polar bonds or not. and whether the molecule is symmetrical. Now, these are individual inorganic molecules. They're kind of standalones. But the question becomes, what do we do if we extend it over a large organic molecule like a protein? Well, basically, nothing changes. You just extend it out. So you're going to have a problem like this, and we'll look at the different aspects of it. So the first thing says is label all the polar bonds with a P. So if we look here, I'm going to go over here and write down my rules. So we're looking for any of the usual suspects. Well, there's one. So we'll have a polar bond here, and this one will be polar. And then here's oxygen, so this one is going to be polar. Oh wait, there's chlorine, so that's polar. So we've labeled all the polar bonds. And again, I'm changing colors as we go so it's easier to see. So then it says label the other ones with an NP. So as we go, all carbon-hydrogen bonds are nonpolar. Anything bonded to itself is going to be nonpolar. So I'm going to make sure I've got everything labeled and I've got all the bonds there, so we're good. And then it says circle the most polar bond. Well, I'm not sure why I didn't do that earlier, but I didn't, so life's good. So if we're looking at it, we've got a nitrogen to a carbon, a nitrogen to a hydrogen, a chlorine to a carbon, and oxygen to a carbon. Well, hydrogen and carbon are pretty much the same. I don't have the absolute values, but I know if I look at my scale that oxygen is the most electronegative, so I'm going to circle that one right there. Okay? Because again, this is best guess. You don't have the absolute values in front of you. Okay, so then we start into the fun part, and by fun I mean, okay, interesting. We're going to look at the bond angle. Well, remember back to your geometry, A, B, C. A bond angle is designated by 3 points, and the center point is the B. We work this identically to what we did before, but we only concentrate on our central atom. We don't care what's around it. We're going to pretend that nothing else keeps going. We're just looking for attach points, okay? So the first one is we've got the bond angle between H1, C1, and C2. So here's our bond angle. So we want to look at it. So what is the bond angle there? How many of y'all said 90? 90 would be wrong. Why? Well, it's written as 90. Yeah, I can draw it any way I want. That doesn't make it right. So what we're going to do is look at the central atom and count the electron regions around it. So it has 2 electron regions. Guess what? That makes it linear. If it's linear, the bond angle is 180. See, that was a trick question. Because you automatically looked at it and said, oh, it's 90 degrees. Nope, it's 180. Okay? Because there's a difference between drawing structures to get them on the page and drawing structures to reflect their geometry. So, for example, for a straight chain hydrocarbon, you may write it like that. But if you were to actually draw it as the shape, it looks like a zigzag line. Okay? More about that when you get tortured in organics. So let's go back here. So on this one, we're going to look at H6 and C4. So we're looking at this angle here. Don't fall for the 90 again. Okay, so everybody think about it. So what's it going to be? A number of y'all may have said, oh, it's going to be 120. Nope. The rule is we're going to go look at this nitrogen and we're going to count the electron regions. In order to do that, we've got to make sure it has all the ones it's supposed to. So it has 1, 2, 3 bonds, and it has to have an octet, so there's a lone pair. One of the tricks is to go and put lone pairs in, because if you don't put lone pairs in, you don't get the full structure. So if you look at that, it now has 4 electron regions, which means we're working with a tetrahedral, which means our starting point is 109.5, but we have a lone pair, so it's going to push down. So our answer is going to be less than 109.5 degrees. All right, so I traditionally work several other ones of this. So let's do the bond angle of OC5H3. And let's do the bond angle of ClC4H4. Since I have that one written at the top, we'll work top to bottom. So if we look at it, we're going to concentrate on the central atom here, which has how many regions? It has 4 electron regions. And they're all bonded, no lone pairs. So that means it's a tetrahedral electronically. So that means it has 109.5 for that bond angle. Okay, so let's look down here at the oxygen C5H3, this one right here. So if we count, we're going to have 3 electron regions, 2 single bonds, and 1 double. So that's 3. So if it's 3 regions, that means it's trigonal planar. So we're going to start at 120 degrees. But remember, lone pairs are going to push more. So this bond angle is going to be greater than 120. The angle on the other side of the triangle is going to be less than 120. So when you look at these angles, there's nothing to them. You apply the exact same rules before, except you concentrate on the central atom. So if you look at it, most of the other ones are going to be tetrahedrals because they're all got 4 electron regions. Now, we're going to, as we continue on and look at hybridization, we're going to incorporate that in. So at this point in time, we've done molecular shape, electronic shape. Oh, I should have started with electronic shape. Molecular shape, bond angles, which comes from the electronic shape. We've now looked at the polarity. It has to have polar bonds and be unsymmetrical. And in the next section, we're going to look at hybridization. So make sure you work a number of these. There are several on video. There are several in the book. The lab you're going to do has a bunch of them, so I would make sure I work on that with enough time to ask me questions, etc., and you'll be good to go.